Ooh, don't want to do that. What if x equal to h1? So in the space h1, we know the function has to be continuous because it has to be differentiable, right? So good. At least we don't have the well-defined problem as you suggested. So what if I have this, and now my L is defined as the maximum or the supremum of any f within H1 of L of f over the norm of f in H1, which is a summation of the L2 norm of the function and the L2 norm of the derivative. So it's a more complex function, more complex problem than I think we can solve in class. But it turns out if you take the in a bounded domain, in a finite domain, this is a bounded function. It's a well-defined functional. That result is going to help us define boundary conditions for our finite element a little bit later on. All right, so this is just giving you some examples of what is space of functions and what is the functionals and bilinear functionals, linear functionals you can define on function spaces. And we are going to define a partial differential equation, including boundary conditions, with the tools we are describing here. Okay, we are going to be defining the solution of PDEs as elements in these function spaces and define a PDE itself using the tools of linear functionals and bilinear functionals. Okay, any questions on these tools we are going to be using next? So the whole construct of finite element and its analysis is built on top of these mathematical constructs. Okay. The weak form of the PDEs is based on these constructs. So to define the weak form, we first need to define a space. X is a functional space. Okay. And the right-hand side, I'm going to write an example. So let's say H1 in the interval 0 and 1 is a functional space, right? And we are going to see how that example turns out to be a differential equation. Okay, and I'm going to define a linear form, bounded. Okay, define a bounded, which means the norm has to be not infinity. Bounded linear functional L and a bounded bilinear functional B. Okay, the example here is, for example, my L of f is equal to the integral from 0 to 1, f of x dx. That's a linear functional, as we have already given here, suggested by one of you, right? Okay, and what if I choose the bilinear functional to be something different? Bilinear functional f and g equal to integration. Because it's in H1, I know the derivatives are well-defined and integrable. So let me take the derivative of f. Actually, it's one dimension, so it's df dx times dg dx. Okay? How do we know this bilinear functional is bounded? Cauchy-Schwarz, right? If this is going to be less than the square integral of df dx times the square integral of dg dx and square root. All right. So this is a bounded bilinear functional, and then a weak form a weak, oh, I didn't want to use this color. A weak form of a PDE, and the critical notion here is boundary condition included is going to be described as B F G equal to L of F. Okay. For any F within this X. Weird, right? A weak form of a linear PDE. Okay. So that's a PDE. It's a partial differential equation, yet there is no concept of differential in this definition here. But let's work through this example to see how it pans out. Okay, so if I take a B of GF equal to L of F for any F here, I'm going to get the integral of 0 to 1 df dx dg dx equal to this thing, which is minus f dx is equal to 0, right? Okay, what if I do integration by parts on the left hand side? Then we get we do integration by parts to this. Basically, I want to take the derivative on df dx and on f, remove that derivative and put that derivative on dg dx. So g gets a double derivative and f gets out of the derivative. So first of all, I get a boundary term, that is f times dg dx at 0 and 1. Okay, and minus, now it's an integral f times d squared g dx squared plus f, well, basically plus 1, equal to 0. Right? Do you follow the integration by parts here? Get a boundary term and an interior term, and I combine with this minus f, so it becomes just a plus 1. Well, this has to be true for any f. Yeah, true for any basis function. That also means, well, what I'm integrating here, because f can be anything, right? The integrand that is multiplied with f probably needs to be 0 everywhere, right? So I get something like I get the differential equation d squared g dx squared plus 1 has to be 0. And okay, this boundary term tells me what? If f has to be 0 everywhere. Oh, sorry, if f can be anything. It also tells me this thing multiplied on f has to be 0, right? On both 0 and 1, because f can be anything, right? So this dg dx at x equal to 0 has to be equal to dg dx at x equal to 1 equal to 0. That pans out to be the boundary condition. That's divergence from what we discussed the last 2 lectures, right? Where the boundary condition doesn't pan out from the integration by parts, but the boundary condition is enforced in this x a priori, right? So in the previous 2 lectures, we have so first of all, we have different types of boundary conditions. We have the value of the solution. I mean, here g is the solution. We have the value of the solution has to be a particular value. Here we have derivative of the solution has to be something. These in finite element are 2 completely different types of boundary conditions. One is enforced through choosing the function space. It's called the essential boundary conditions. That's what we have been doing last 2 lectures. And this type of boundary condition that naturally comes out of the bilinear form, that naturally comes out of the weak form, is called the natural boundary conditions. Essential and natural. Essential is, for example, let me change it even different color. If I say, okay, I'm not allowing my space to be H1, but a more restricted version of H1. It has to be H1, it has to be the intersection of H1 functions and functions that are equal to 0 at both boundaries. Okay, if I set my X to be that, that's also a perfectly valid vector space, a perfectly valid linear space. If I do that, then because my F is in that space, this boundary term disappears without any requirement, right? This boundary term disappears by itself. And the boundary condition is enforced directly by the fact that G has to be in the function space. Any questions on this?